Welcome to this ThinkSmallCell Editorial webinar, where we're looking at Cellular Enterprise Solutions, and that's specifically the in-building architectures available for cellular wireless systems. We're not looking at residential buildings, we're not looking at outdoor or rural, but pretty much every other building would be covered by one or other of these technologies. And what we're aiming to do today is to lay out what these different technologies are. Firstly, we'll briefly outline the problem, and then we'll run through the various architectures available. Follow that with a few considerations and discussion of the related issues and the trade-offs between them, and come up with a conclusion. We've got quite a packed agenda today. There's a lot of material in this session, but if we have time, we'll take one or two questions at the end of the session. So you're welcome to submit a question at any time during the event, simply through the panel on the right-hand side of your screen. So why is the problem of cellular coverage or service in building getting worse? Well, I look at two particular factors. There is an increasing demand where we're using our smartphones more. There are many more smartphones available, something like 970 million units shipped this year, last year alone. And each of those services that we're using on the smartphones are using increasing amounts of data. The most specific service that's causing a problem is that of mobile video, which is being viewed ever more frequently on the internet and specifically on mobile devices. And at the same time, we've got some technical issues, some technical barriers that make it more difficult to serve our customers. Buildings are being constructed from materials that aren't friendly to RF frequencies, and it's more difficult to penetrate in building. Although some lower frequencies are available, there's quite a lot of spectrum at high frequency, specifically available for capacity, which really can't penetrate in building as reliably. And last but not least, there's the issue of 3G cell breathing. So that's where a cell, if it's congested, if it's busy, will effectively reduce its range in order to serve the devices that are connected to it. And so those at the edge of the cell are more difficult to reach, typically in building, are the ones that suffer. So what that's leading to is customer dissatisfaction. There is still increasing demand, and we can't see that finishing. And that's leading, therefore, to various business cases being developed where we're looking at sources of funding, not just from the network operator themselves, but perhaps from the building owner. And perhaps it's no surprise today that there's this disparity between in-building service. Something like 80% of the mobile data traffic is consumed indoors, but in terms of infrastructure that's specifically deployed in building, the infrastructure spend is less than, considerably less than that. 12% is the estimate that we've seen from ABI and Infinetics. Now, a practical example of this was at a recent conference I attended where we were talking about 5G, but just the practical use of the advanced phones that we had in the conference itself. As you can see from this slide from Murray Rumney of Agilent, we could barely get a 2G service in the auditorium. I'm not particularly picking out that event. I think I've seen that happen a number of times. So what we really need to do is move the signal indoors, and we need to have extra antenna indoors. There's an immediate benefit of that in that the short range means that you can use much lower RF power, and so your smartphone itself would have a much longer battery life. Now, I know people tell me that the percentage of battery on a smartphone that's used for the radio versus the screen these days is significantly less, but I would still say my own experience is that where it's more difficult to get a signal connectivity, then the battery life is reduced. But there's another subtle benefit here indoors in that the higher quality of the radio channel to the device means that we can take advantage of higher modulation rates and deliver very much faster, higher speeds and quality of service to the users. There's also the benefit that we can have high frequency reuse, which ultimately delivers that greater capacity that we need. And that lower signal power also means that there's less interference with the outdoor network. And that's, surprisingly, that's also helped by the fact that these buildings have more RF isolation with the new construction materials I mentioned earlier. Another factor indoors is that devices typically are moving quite slowly. You're walking around the building, you're not driving in your car at high speed down a motorway. So there are fewer resources required to deal with that fast mobility. And instead, we need to handle issues around signaling traffic, which may peak at certain times, and also where there's a greater range of peak to mean traffic in various parts of a building. So there's a whole variety of use cases that we'd need to consider, and some buildings we'd be looking primarily for capacity, an indoor stadium where you have many people sitting as closely together as they possibly can, all with their mobile devices wanting to send and receive data. And at the other extreme, perhaps more of a coverage situation, a large warehouse or a hangar where you've got relatively few people, but they do need to be connected. And I've shown just examples of a variety of use cases that might fit on that axis in different ways. Now, these will vary widely depending on the particular circumstances. And I think another factor to take into account is the impact and availability of good Wi-Fi service, which has a strong bearing on the traffic demand. So given that you want to deploy a cellular or mobile solution indoors, there is a very confusing and large range of choices that you can make. I think before we get into the more traditional cellular systems, the wired ones, it's worth pointing out that repeaters have been seen as a popular or a quick fix. And I would look at these as three categories. The left-hand category is, frankly, not a good idea. It's the typically lower cost, potentially lower quality solution that may well solve your problem, but it's likely to impact the network and certainly impact the service for others. This type of product is illegal, and we do see enforcement action being taken simply because they do cause so much disruption. The second type is a more compliant and friendly type of repeater. These are products which you would be able to buy in shops in certain countries. They're legal in North America, for example, and they would work with multiple operators, and some of them work with both 3G and 4G. And you don't need to buy them with or through your own network. So they're a quick fix, and they may well be suited for situations such as your holiday home or your log cabin, where it's just a low signal level that you're trying to deal with. And the third type of category is a more network-specific product. And these are products which are sold or subsidized directly by the network operator. Usually they just work with one network, and they can be remotely controlled or managed by the network operator if they cause a problem. And those types of products are legal in most countries because they're being done and sold through the network operator in cooperation with them. But an important point here is that repeaters themselves don't add capacity. And so whilst they might be useful in a low traffic, remote or rural area, they can be counterproductive in more congested or high traffic areas. The issue is that because they're not adding capacity, if you're grabbing more resource, then somebody else is getting less. And there have been situations where enterprises with their own repeaters deployed are getting a reasonable service, but customers outside on the street are not being able to access the base stations because the signal is being drowned out by the repeater. So we have seen most operators look to replace their own repeaters in those kind of scenarios. Now, moving on, we're really looking at the rest of the presentation around a wired wireless base station solution. And when we look at that, we see that typically a standard base station comprises three components. It would have some backhaul through normally Ethernet these days to a baseband unit that's full of high capacity digital signal processing. That's then connected through a digital interface to a radio head, which converts that into a radio frequency, and that is then sent and received through an antenna. There's a common standard for the interface between the digital and the radio head, the CPRI interface, which is used by a number of vendors and to interface their products. And these three components can all be shrunk and provided as a single product, which is what you get with a small cell, or they can be distributed. So you can have remote radio heads or a distributed antenna system. And we'll just work through the different architectures in the next few slides. Broadly speaking, I've defined three categories here. The more traditional small cells that we've been working with for some time, a distributed radio system, sometimes called a cloud RAN, and then a distributed antenna system. And there are a variety of products where I've struggled to just pinpoint exactly which of these three categories they might fit. But I think these do serve a good purpose to distinguish between the various systems. So let's look at how that centralized versus a distributed functionality might be applied. Now we start with the traditional macro cell where it's centralized in one place. The baseband, the antennas, the radios, they're all in one large box, and that's covering a wide area. Oops. And then what you can do is, instead of connecting the macro cell to a cell tower with an antenna at the top, you could connect it through a distributed antenna system into a building, and effectively the building has a complete antenna system throughout it. So those antennas are much closer to the end users. You can separate out within the macro cell the radio part and the baseband processing, and that's what we've seen with the CPRI interface connect through to remote radio heads that might be deployed nearby. And again, there are in-building systems that have that architecture. The other kind of extreme, I suppose, is the standalone small cell, which has all of the functionality miniaturized and deployed at the edge. So every node that you see deployed around a building would have the full function of a base station. And where you have several of those, you may either have some peer-to-peer functionality that's coordinating how they operate, or you may deploy a local controller, typically in the machine room, in the basement, which manages and coordinates and optimizes the operation. You can also have a distributed radio system, which is where, again, you have a lot of antenna deployed around the building, but more of the radio functionality is deployed there, whilst the baseband is coordinated centrally. So there's a lot more centralization of the baseband processing. Another way of just walking through that distinction is to look at this chart where I've shown the small cell has the baseband processing, and it only has a very low speed backhaul requirement. It doesn't need fiber to every small cell. That's something that's been proven and is popular for residential small cells, where femtocells have been deployed in millions of locations and don't require really any high quality backhaul connection. Now, if we have a number of small cells deployed in a building, again, they would have the baseband processing located within them, but you may have either some peer-to-peer functionality to manage them or a local controller. And then we move up to the next level where what I've called a group controller might have some baseband functionality in it. And so, as you can see, there's a thicker line and a larger amount of data traffic traveling to what is now a much simpler radio head deployed around the building. And that's actually fairly similar to what we see with solutions that are derived from existing base stations or microcells, where we've split out a remote radio head which converts the signal into RF, and that might well be deployed with a box in the closet on every floor or every other floor, connected by fiber to a base station in the basement. And last but not least, we come up with DAS. There are a variety of technical solutions there, but some of them do require dark fiber all the way from the base stations that are deployed centrally through to a number of antennae distributed throughout the building. So let's just walk through each of these sections and look at how those are realized and some of the products available. So I've said enterprise small cells have that complete cellular functionality on board. Where you have a number of them, you might have peer-to-peer negotiation. An example of that is where, for example, in a canteen, you might have a lot of people move in there at lunchtime, a lot of traffic generated, and so that cell might reduce its power level, reduce its range, and negotiate with its nearby neighbors for them to increase their range and their power capacity, effectively managing the traffic to hand over and be balanced and shared out between them in an efficient manner. And last but not least, you can have a local controller that's handling that process, and that's coordinating centrally between multiple small cells. And one of the advantages of doing that is that the multiple small cells can appear as a single virtual cell, so that your phone doesn't need itself to manage a handover when it's moving to another cell nearby. That can all be coordinated centrally. And that clearly helps reduce the chance of cold drops and other issues. So the physical products that you see here are actually quite similar to residential femtocells. They may have a slightly higher RF power, I'd say up to 250 milliwatts at the most. And that allows them to provide that wider area coverage for less dense buildings, the warehouses and those sorts of use cases. They can typically handle higher traffic capacity than a residential product, somewhere in the range of 16 to 64 user. We have seen products that have higher than that, but I think that's fairly typical. And one of the reasons for that is that you want the unit to fit within the power budget of an Ethernet cable. So you just have a single cable providing both the backhaul and the power to the unit. And these are typically designed to be pretty unobtrusive and you really don't notice them. So they're similar in shape and style to a smoke detector or a remote alarm. Perhaps an unusual format here is that Cisco have their own Wi-Fi, enterprise Wi-Fi product, the Aeronet 3600 series. And what they've done is design a module that just plugs into the unit that allows it to be upgraded to have 3G as well as Wi-Fi. And again, shares that same power over Ethernet for both backhaul and power. So it's a very simple, straightforward upgrade. And because the range of the 3G signal is much greater than that for just a Wi-Fi system, you typically wouldn't need to upgrade all of the access points. We were also seeing come onto the market a number of multi-standard or dual mode products. So this one from Alcatel-Lucent that's just in the trial stage can handle both 3G and 4G and be remotely configured to be either or both, as well as handling Wi-Fi. And I think this is certainly the highest capability that you'd want if you were looking for a product that was fairly future-proof. Now, I would describe those as enterprise small cells. But the term picocell also comes up. And my view, which isn't shared by everybody, is that a picocell is really designed as a scaled down macro cell. So the origins are from the technology, both the hardware used and the software that's used in the larger parts of the family. And that can be a good or a bad thing, depending on how you look at it. These are perhaps more visible or more noticeable on outdoor deployments than indoor, but they equally used in a number of indoor environments. Another distinction is that the small cells, or the femtocells certainly, were designed to use an IUH interface and have a small cell gateway, whereas a picocell would typically, for 3G service, use an IUB interface into the RNC, and that gives it the possibility of providing soft handover, which isn't a feature of IUH. These picocells that I've been shown often have quite high capacity. So for 4G service anyway, we're talking 128 or anything up to as many as 400 active users. And one of the marketing points of a picocell is that it gives you a seamless coordination with the external macro cells from the same vendor. So that can also work against them, because if you were to put picocells underneath a different RAN vendor, perhaps that's a less common scenario. Equally, there is always the question of price. I think there may well be some savings by using the same vendor and the same systems, the same planning tools and so on. But a key factor will be the cost of that. Some examples of products available. Ericsson have recently announced the 6402, very interesting product, highly capable. Huawei, Nokia, ZTE, and others have similar products. Now, I think the common view is that if you want to extend coverage by using small cells, then you would simply deploy more. It doesn't matter, the cost of each small cell is not particularly high, so you can simply deploy them in almost a similar way to enterprise Wi-Fi. And a use case might well be a large warehouse where, although you don't have significant usage, coverage is essential to reach all parts of the building. But one thing I saw was relatively unusual was from a company called Comba, where they're offering an extender product that isn't a full small cell, but connects by Ethernet through to the master small cell, if you like, and just allows the signal to be transmitted and received in parallel over a larger area. And I think while we're talking about antennas, it's worth saying that a good antenna will make a dramatic difference to the performance of any in-building system. This particular product I'm showing here, for example, is something that could be would be visible inside a building, but you may have the small cell installed in the plenum above a false ceiling or hidden away otherwise, so it could reduce the visible footprint. But these products do achieve very high range and performance and can even handle 2x2 MIMO by polarizing separately the horizontal and vertical signals being transmitted. Now, once you get into a larger number of small cells, you may have a local controller, and this is a chart from SpiderCloud that shows the standard Ethernet wiring that you would have within the building. It could even share a VPN if you have IT infrastructure. And then in the basement or in the machine room, the data center, you'd have a services node which would provide that coordination between the small cells. And an additional advantage is that you can run applications for your enterprise on that box. So now we move on to a distributed radio system. And I think the most visible ones that we've seen are the Huawei and Ericsson products, which have evolved from their existing base station designs. But it's also worth looking at a new product from Airvana, which was launched recently, that's designed specifically with this architecture in mind. And these products are aimed at medium-sized buildings where it's perhaps not large enough to justify a full distributed antenna system, but where it's felt that the small cells on their own may not be enough. Now, Huawei's solution here, as you can see on the left, comprises a rack with the baseband processing connected by optical fiber to a number of these smaller boxes that would be in a closet, maybe every other floor in a tower block. And these then connect to the radio heads, which have space inside them for a 3G unit, an LTE unit, and a Wi-Fi radio. And these can be deployed both within an office, and I understand Huawei have deployed that in their office here in the UK, or in a mall or an airport. And the largest deployment I've heard of is at Beijing Airport, where there's something like 2,200 radio units deployed. Now, that doesn't mean that there's 2,200 radio sectors of capacity. Many of these radio units may be paralleled up just to provide coverage. Ericsson has a similar solution here. It's called the Radio DOT. I believe that will come to commercial launch next year. And that, again, has a digital baseband unit that's connected by optical fiber to a box in the closet, and then through an Ethernet Category 6 cable to the actual antenna unit. Now, both of these systems are single operator, so these connect to one base station, so you would normally expect them to be only providing the signal for one service provider rather than multiple. This is a new system from Airvana. It's called OneCell. It is a 4G only solution, and it's been designed from the ground up, very similar to the previous architectures we've just seen. But it can transmit the signal over IP. It doesn't necessarily need fiber. So although these boxes in the middle are simply Ethernet switches, they're not remote units, and they don't have any intelligence. Everything is either in the baseband controller or in the radio points. And each radio point can potentially be a different sector, so it can add a lot of capacity. And one of the features that Airvana are keen to point out is that by using the centralized baseband controller, they can handle the interaction at the cell edge between multiple radio points very efficiently. And so you get not just a good signal when you're close to a radio point, but when you're halfway between one and the other. And unusually, perhaps they've also designed a solution where you have multiple service providers. So what they've done is provide what I've called a toaster rack that allows multiple cartridges or multiple radio points to be connected to the same antenna. And these would perhaps be installed again in the plenum or in the false ceiling slightly out of the way, and minimize the impact of what's visible. But at least it does allow a multi-operator in-building solution. So then we move on to a full distributed antenna system. And I think one of the things I've discovered from talking to a number of DAS vendors over the last few weeks is just that there's such a wide variety of different architectures and products available. But in general, the major advantages of a DAS are that it's multi-operator, it's multi-vendor. You can have a number of different RAN vendors connected to it, different operators. It can be any frequency band you like, and it can support the different technologies. What a DAS system doesn't do, though, is it doesn't add any capacity by itself. Although it can carry the traffic from a large number of base stations. If you do visit some of these stadiums which have huge DAS systems installed, you can just see machine rooms with racks and racks and racks of large, base station equipment generating a lot of heat. So it's something that's got a lot of advantage, but it doesn't add capacity itself. It's typically independent of the Wi-Fi system, and it's not cheap. We're usually thinking in terms of hundreds of thousands of dollars to begin with, and it's really not unusual for a DAS deployment to be $1 million. It's important to include the cost of the operator's base stations in the budget just as much as the DAS system itself. Now, one important distinction perhaps is between a passive and an active DAS system. So particularly in previous days, a passive DAS system would simply be an antenna. It was carrying the radio signal often over thick coax cable around a building and using splitters and RF splitters to radio heads in various places. What we're seeing now is more of an active DAS system where the signal itself is carried on fiber, and that can allow it to be transmitted over quite long ranges, distributed over quite wide areas. And it's also easier to pull fiber through buildings than perhaps it was the thicker DAS. So I said that not all DAS products are the same, and clearly if you were wanting something that delivered very high capacity, the highest capacity for a stadium, then you would use radio nodes and equipment that was of a much higher standard and probably higher cost than something that's simply providing an average capacity solution for an office building. There are a variety of different technologies used. I've talked about some of these older passive coax systems. I think they're rarely deployed today. And what we're seeing is dark fiber used, which in some cases would carry the RF signal all the way through to the antenna. So the whole system appears very transparent to what it's carrying, whereas other systems digitally encode the RF and send that digital signal to the closet where it's then remodulated up to RF. And we also have some systems that are effectively digitally end-to-end and almost look similar to the distributed radio systems that I spoke about earlier. I'm also surprised at some of the levels of high power that can be used. So where we've talked about in building small cells being perhaps 250 milliwatt radio power, DAS systems can be up to 5 watts per radio node. And again, it depends whether you're looking for capacity or coverage. Some of the recent improvements that have been made in the latest DAS products, certainly the range of frequency bands that can be handled is quite important. Some of the systems that might be deployed in the field today would have been designed for the spectrum that was in use at that time. And one of the problems is that as new spectrum becomes available and allocated, those systems may not be able to support it. So what we're seeing is the later DAS systems have this wide range of frequency band support. And this example here from CommScope, whose solution allows you to allocate any blocks up to a total of 300 megahertz of usable spectrum in the range shown, which covers pretty much everybody's requirements. And that should increase the lifetime of the DAS systems that are deployed today. We're also seeing use of Cat6 cabling, certainly for the last few meters within the same floor, and that would make it easier than having to pull fiber or pull thick coax all the way through to each radio node. There's been some improvements and simplification of the installation of DAS. Now, I'm told that the cost of a DAS project might well be 50% project costs or more rather than the capital equipment. So anything that can be done to make it simpler to install is a good thing. A number of vendors have features. I've seen one that guides the cable connection. So as you plug in the cables in the switch panel, lights light up to show exactly where you should connect them, and there are electrical tests to validate that you've done it correctly. We've seen some planning and documentation tools that are very easy to use. And then I'll just expand on these last couple of points around bypassing the inefficient RF and configuring some of the sectors of a DAS system. So here's an example from TE Connectivity and Alcatel-Lucent, where what they've done is look at the normal connection into a DAS system, which on the top left of the screen, it shows there's a full radio head. So you've got a base station that's generating a full RF signal, just as it would to connect to any antenna. And that's then connected through this point of interface, which is an attenuator that reduces the RF signal and then converts it into digital form for that to be transported throughout the building. And what they've done is effectively remove the radio head, so you don't take the signal and convert it to RF and convert it back. You just directly accept the CPRI digital interface into the DAS system. Effectively, it's making it look more like a distributed radio system in my book. But the advantage of this approach is that the central unit can also accept RF signals from other operators or other vendors and mix them in, which is quite a powerful solution. And the benefit there is that not only do you save by not having to buy unused or unnecessary RF parts of the macro cell, it doesn't generate so much heat and doesn't consume so much energy, so you don't need as much air conditioning. And a second point to look at is the concept of configurable sectors. Now, one of the benefits of a small cell solution is that every small cell is its own sector. So as you deploy a large number of small cells, you inherently have a lot of sectors, a lot of capacity, because each sector can be used to its full potential. But a DAS system often shares many RF heads to a given base station sector. And the problem then is that as the users, the traffic moves around the building, you may want to direct the capacity from one sector to another to make best use of available resources. So you could do that manually by literally plugging and unplugging cables at a patch panel. But some products allow this to be done under software control through effectively electronic switching. And a more recent product from Dali Wireless has what they call RF routing, which allows all of the RF signals that are coming through the system to effectively be directed to any radio head, anything with an IP address, as they say. So that could be used to reconfigure. An example here is where you have a stadium that's used for a sporting event one day, and then that central sporting area, it becomes seating for a concert the next day. And by being able to press a button and switch between 2 or 3 predefined configurations, that may well be a useful feature. But in my book, it's unlikely that there would be frequent changes of the different sectorization. We're certainly not at a level where a self-organizing networks system could remotely control that. And it is questionable who would pay for the engineering time to actively manage it. It would presumably have to be somebody in the operator, but if you've got multiple operators sharing these different sectors, then that has to be coordinated. So let's just have a quick look at some of the considerations that you might take into account when selecting between these different options. One is certainly the cabling requirements. And for a small cell with just the need for a simple Ethernet cable that perhaps provides power as well, I think that's clearly a very simple and easy to deploy solution. As you get into more of these distributed radio systems, you're looking at something like fiber to the closet on the floor, and then some Cat6 dedicated cable. It's not carrying Ethernet, it's carrying a special signal direct to the antenna. And with DAS, there are a variety of technical solutions. Some products do require fiber all the way to the radio heads, and in fact have a composite cable that's specially designed that has both fiber and copper wires to carry the power. There are other solutions that are more like the one above, where you've got fiber to the closet and Cat6 for the last part. So that specific type of cabling may be not just expensive to buy, but may require some specialist knowledge to deploy. Second factor, I think, is around the radio technology that you want to use. So today, I would argue that predominantly it's about making voice calls indoors is the strongest demand, but we can expect that to move towards 4G and to provide voice over VoLTE over the coming years. There are many 3G products available today, and certainly from a small cell perspective, the latest products that can do 3G, 4G, or some that are just 4G only are either available or at an advanced trial stage. So I think there's still a large market for 3G, but when you're looking at deploying something today, you want to look at how long it's going to last, what the lifetime is, whether you can accommodate both 3G and 4G and remotely reconfigure the system to allow the frequency or the band plan to change. Now, many small cells originally were designed with minimum cost, but for enterprise deployment, we've seen the capability for this remote configuration being built in. In the past, some of the DAS systems could perhaps only support certain specific frequency bands, but I think we've seen that trend change so that they can support any technology natively and accommodate a wide range of frequencies. Now, a third point is whether it's useful to have some applications on site as part of the system, and whether caching some of the data may be a useful feature. So you can, with some small cells, offer a local data caching feature that's transparent, and that can significantly speed up the end user performance, the latency, when accessing common types of data. A local in-building controller may well be able to host some specific applications. And to be honest, I haven't seen either of those features with more of a DAS approach. And it's important to look at how enterprise Wi-Fi would coexist with these solutions. For small cells, a combined Wi-Fi and small cell unit is quite a common product. They don't interfere at the kind of RF performance power levels that we're talking about. And typically, you're looking at enterprise-grade dual band 802.11n or AC or both, which allows a significant amount of throughput. And that's where the 1 gigabit Ethernet backhaul capacity is quite important. You would easily consume the 100 megabits if that was all that was offered. So typically, DAS systems don't fully integrate with Wi-Fi. Some of them do provide an IP connection for backhaul, but the view really seems to be that the footprint of a Wi-Fi access point is quite different to a DAS radio head, and therefore it doesn't necessarily make sense to co-locate them. I think a very important topic really is whether a building owner is looking for a multi-operator solution rather than a single operator. If you're serving guests and visitors, or even if you're a business that encourages your employees to bring their own device and their own network, then it's helpful to support as many networks as possible. Now, technically, that can be done through commercial roaming. There's no technical reason why a single network deployed can't do that, but commercially that doesn't generally happen. So operators may prefer just to deploy a solution that's locked to their network, and that allows them to differentiate with a higher quality service and potentially win more business and lock in some larger enterprise contract. And that would perhaps encourage them to subsidize the deployment of the system. So there are some trade-offs there between whether you want that single operator or that multi-operator approach. And whilst Wi-Fi itself may be technically neutral, I think in some cases that can still be commercially locked in to one or other operator at times. And last but not least, I think operators have a perception of how much risk is involved in deploying different types of product. If they stick with the same supplier for both indoor and outdoor, they may feel that they have fewer compatibility issues. They may feel, handover works well. They can stick with the same planning tools, although I'd argue that indoor businesses typically do need a different planning tool. And again, I would see different operational processes and staff training being required, even if you're using the same supplier for your infrastructure. So when you look at different suppliers, and I'm talking not just about equipment vendors, but also third-party deployment integration specialists, what you may find is that they come with more innovation. They're able to move more quickly, and by being able to use that resource, it allows operators to scale more quickly and grow faster. Potentially through competition also at a lower cost. So a quick summary table. Really small cells, highly scalable, very simple, very cost effective. But you may need extra nodes. They're not inherently multi-operator, and they are perceived as new technology. A Cloud RAN or distributed radio system would give you probably the highest capacity possible, but again, they're typically not multi-operator, and they would require a certain amount of fiber cabling. DAS systems, well, multi-operator, multi-vendor, perceived as very compatible with the macro network, but there is more cabling issue required, and they're perceived as a higher cost because you need the full macro cell component as well as the in-building equipment. That cost, of course, can be shared if you've got multiple operators in the same building, which may make it more attractive. So one way of looking at which type of solution might fit a particular building, it does vary with use cases, might be by the number of employees. And as you can see from this chart, you might start with a small enterprise, small cell. You might then have multiple units deployed as you get bigger. And then at some point, and it is highly dependent on the use case, then you're looking at a group of small cells or a distributed radio system or a full DAS system to be deployed. So in conclusion, I think that as we increase the demand for the quality of service and the speed of service and the capacity available, there is a need for more radio units to be deployed. And I think that's generally agreed, so that most operators have a roadmap to do that. A small cell approach does introduce new vendors, new technology, new processes, but it also introduces low cost. A distributed radio system promises that high capacity, and a DAS system retains the existing vendors, allows you to share the infrastructure and share that higher cost, but it is higher, I would say. And the choice in each case will depend on the specific parameters, everything from building size, the importance of that multi-operator requirement, and what Wi-Fi system is available or integrated. And last but not least, of course, the budget available. So for more information, there is a white paper that, there is a white paper available from Alcatel-Lucent. You can download that from the ThinkSmallCell website, and we'll send you a link to it as part of this event. There's plenty of information on each of these products from the different vendor websites, and of course on ThinkSmallCell we cover this topic as well. I'd like to thank our sponsor Alcatel-Lucent for making this editorial webinar possible. If your company would also feel they could benefit by sponsoring one of these webinars, either presenting yourself or supporting our in-house educational content, then please do get in touch.